Hello, everyone. I hope you are having a wonderful conference so far. My name is Pranay Bakre. I am a technical marketing engineer at ARM. And today we are going to talk about object detection and real-time analytics at the edge with GPU-enabled Kubernetes cluster. So this is the agenda of our session. We are going to be talking about the challenges, a little bit of history on edge computing challenges. Then we'll move towards how the edge devices or the gateways have evolved over the years. We are also going to talk about Project Cassini, which is an open and collaborative, it's a standard-based initiative from ARM to deliver a cloud-native software experience across a secure ARM edge ecosystem. Then we are going to talk about how containers at the edge with AI, with GPU solve some of these problems. Then we'll make a segue into the actual use case, intelligent video analytics with Nvdia DeepStream with K3s, and how DeepStream and K3s together make up for a compelling solution to be leveraged in this scenarios. And then the architecture of the use case that we have built. And finally, we'll have a live demo to see the actual use case in action, right? So what are the some challenges that I think most of us know so far at the edge that we face, right? So first of all is the resource constraints. So these small edge devices often do not have the huge compute capacity of their cloud counterparts. Now, these devices are not designed to be managed at scale in resource constrained environments. The second one is latency and bandwidth requirements. So I think we all know that applications deployed at the edge that might be sensitive to latency and bandwidth requirements that are not fulfilled by cloud. Then the third is data proximity. So there are edge deployments that are required to be close to the edge to be able to make that intelligent data processing decisions close to the source. In many cases, this means providing AI and ML close to the data source to be able to keep up with the growing data being generated. Then there is scale. Similarly, I mean, the scalability of these IoT endpoints and how that influences the aggregation that needs to happen for these edge devices and these computing platforms is important. And last but not the least, security. Security principles from the data center don't necessarily apply as is for all edge scenarios. And also, since the device landscape is so fragmented that there is a growing need for standardization of security principles at the edge that's integrated between software and hardware. Okay, so now let's look at evolution of the edge. So what we are seeing with all of this is an evolution of the edge. So historically, the fixed functions performed outside of the data center included some sort of network function management. And from a software perspective, it's all a single purpose RTOS or real-time operating system environment. What's changing in this stack is becoming more of an intelligent computing platform, ultimately leading to the emergence of what we are calling the AI edge, which can perform high-level functions to be able to make those timely decisions. Now, performing these intelligent functions at the edge has many benefits. It significantly reduces backhaul to the cloud. It cuts latency, improves reliability, efficiency, and security, the challenges that we talked about. And in a world where models need to or may need to evolve in real time as insights from these global device deployments come first. So moving on to Project Cassini, right? So to help this AI edge transition, ARM announced Project Cassini, the open collaborative standard-based initiative to deliver a cloud-native software experience across a secure ARM edge ecosystem. Now, Project Cassini is built on three foundational components. The ARM System Ready program that launched last week at ARM's annual conference Dev Summit. It's a foundational certification program with the vision of enabling software to work seamlessly across a vibrant and diverse ecosystem of hardware. Now, it builds on the existing server ready program, setting the standards for a broader set of devices, initially in the infrastructure edge and IoT edge segments. The second one is security APIs and certification programs trusted by developer communities and across workloads through PAC certified and Parsec. Parsec is platform abstraction for security. It's an open source initiative based on the PAC API. It provides secure ROT abstraction and common runtime security services for applications in an architecture agnostic manner. ARM has contributed Parsec to the Cloud Native Computing Foundation as a community sandbox project. And the third one is reference solutions for a cloud native edge developed in partnership with the ecosystem. So now let's talk about containers at the edge and AI with GPU. So why containers at the edge make for ideal candidates to run at the edge, right? We start with that. We all know that those are lightweight and highly portable. Deploying application in form of containers and then eventually microservices makes much more sense since because of these edge, how these devices have the compute capabilities. So containers make an ideal candidate for that. In terms of taking advantage of the GPUs, there are the heavy workloads, especially the AI ML workloads. Containers can take advantage of devices like Jetson, Nvdia Jetsons, the Jetson family platform, Jetson Nano. These have those GPU capabilities, and containers can take advantage of those GPUs to process these high performance workloads. Then latency, since it's all close to the data source, we observe a much more lower latency and than dealing with a cloud controller here, since all of that is local. And that actually makes sense for local AI inferencing and analytics. So analytics will happen at the edge location using these containers and leveraging the GPU workloads, the power of it, and can be turned all locally and done the simulations and analytics at the edge. That reduces the data hosting costs in the cloud, and which makes a much more compelling argument to have everything at the edge location. And last one is it's secure architecture, since we do not need to manage a lot of security aspects that come with the cloud, but we need to focus on the edge location with physical security and device security. And we saw with Parsec and Project Cassini, we can achieve those aspects of it in a cloud agnostic or in a vendor agnostic manner. So now, what's an intelligent video analytics with the DeepStream and K3S? So before we go there, we need to understand what is Nvdia DeepStream and what is K3S, right? So I think everyone knows about K3S. So let's talk about Nvdia DeepStream for a minute. So DeepStream is an SDK that delivers a complete streaming and analytics toolkit for real-time AI based video and image understanding and multi-sensor processing. So it provides a set of features out of the box to develop those building blocks for building or creating deep neural network platforms. So you don't have to, so users don't have to start from scratch. They can take those building blocks and can build on top of that. It also provides some plugins to bring these complex, so AI and ML, I mean, these tasks are complex in their own regard. So so DeepStream, it provides a set of plugins hardware accelerated plugins to bring these complex processing tasks into a stream processing pipeline. And container support for, so all of the Jetson platforms, including Jetson Nano, Xavier NX, are all supported by Nvdia DeepStream, and those containers can run on top of it. So as we know, that K3s is a orchestration tool based on Kubernetes, and it's an upstream distribution. So with K3s, we can achieve quick and reliable application deployments in those resource-constrained environments, because K3s has been designed to work on edge and cloud devices as a whole, right? It has been designed to work on these low memory footprint devices, and it's a production-grade distribution. And K3s, it provides access to these hardware resources for these Nvidia GPUs through the device plugin framework. So it's based on Kubernetes, the device plugin framework, but K3s enables that, and it provides a mechanism for these containers to leverage the power of these GPUs. So these DeepStream containers deployed in a K3s cluster and running on an Nvidia Jetson platform, in this case Nano, would give us a mechanism and means to achieve these orchestration level details and performance from on these small devices. And since these analytics and object detection, I think we talked about it earlier, will happen directly at the edge devices or at the edge location. So everything will be self-contained, and it can happen at any different location. So there are multiple real-time applications to it, like a toll booth where a camera is pointed to the highways, and it can detect a lot of things. It can provide a stream to these DeepStream SDKs running on a K3s cluster, and that all can happen at the edge location. Okay, so now let's talk about the architecture of the use case. So here you see an edge location with a camera that's providing multiple video streams, and it's a USB camera that's connected directly to the Jetson Nano. Now you see two different video feeds. So what those mean is, in the live video feed, the camera is pointed towards a parking lot, and it's able to detect whatever objects are there in the stream, and it's providing it to the Jetson Nano. In the second one, the CAN video feed, so in that case, a video is playing on a monitor, and the camera is pointed towards that monitor, and it's recording those streams and then sending it to the Jetson Nano. Now, let's talk about the right-hand side. So on the Nvidia Jetson Nano, these platforms run a flavor called L40, or Linux for Tegra, that's based on Ubuntu 18.04. And this operating system, along with the CUDA X drivers, so here we have the CUDA 10.2, comes as an SDK and is packaged into what's called Jetpack. So which is it's a comprehensive software stack for the Jetson family of products, in this case Jetson Nano, and has all these dependencies and libraries built in. And we are using the Jetpack version 4.4. Then we have deployed a K3s cluster. But before that, we have to use NVIDIA Container Runtime. So NVIDIA introduced that with Jetpack 4.2, and it's a container runtime that can take advantage of the GPUs that are running or that are part of the Jetson family of products. So, and eventually, we have the DeepStream L40 containers deployed as pods on these K3s clusters, and we'll see the live demo on how that's done. Okay. So now, okay, yeah. So this is the environment setup. So here you see 4 nanos. So for this use case, we are just using one, but this is part of the entire setup that we have. And it's a Jetson Nano developer kit, one barrel jack 5-watt 5 volt 4 amperes power supply, 1 Gbps Ethernet switch, UTP and Ethernet cables for connectivity to these nanos. The webcam that I talked about, camera is connected to the nanos with the USB. Then is a display that's attached to Jetson Nano via HDMI. So we can see when it detects any objects and what's happening in the video frames. And we are using the DeepStream SDK 5.0 version. So now, right. So now it's time for the demo. What we're going to see is, first of all, we've connected to the Jetson Nano, and here we are going to see what is the versions of the softwares, and then we are going to quickly install a K3S cluster on top of it, then deploy the Jetson DeepStream L40 containers, and then we'll see how they execute on and how they detect the objects and does video analytics. Okay. So here, let me just go quickly and show you the versions. So here we see that the Jetson Nano developer kit we are using L40 and Jetpack 4.4. CUDA version is 10.2 as we talked about, and it's based on Ubuntu 18.04. So now, right. So this is just the Docker version and info, rather, that what's the runtime. So right now, the default runtime is run C, and the available one is Nvdia as well. So we are going to change it to Nvdia container runtime in the Docker daemon file, so that when we deploy K3S, we can use that runtime. So it's a simple one-line change. Right, so now we've changed the default runtime. We are now going to restart Docker, and right. So now the default runtime is changed to Nvdia, and just install curl because this is the first time we are doing it from the scratch. So here, so right, so this is done. All right. So now we'll install K3S on top of this, and here, so while this is running, I'll explain. So K3S by default comes with containerd as its runtime, but it allows you to change the container runtime to Docker, and you can use to you can install the K3S and point it to your existing runtime. So it'll let you do that. So with this install underscore K3S exec, we have specified Docker, and we know that internally we have changed it and pointed it to Nvdia container runtime. That's the default one in place of run C. So it happens pretty quick, but maybe it's taking a while. So while it's downloading, we see that we are using the 18.9 version of K3S here, the stable release, and it is already starting K3S on top of it. So, okay, all right. So now that's done. Let's take a look at using kubectl, the version of the nodes, and we see that it has deployed 1.18.9, the stable release of it, and it's based on ARM64 since we are doing it on Jetson Nano. All right, so now let's see. All right, so what we are doing here is we are executing a default or a default container, which the device query, which will tell us if it's able to access these GPUs on this Jetson Nano. So since we've installed K3S on top of it, and now we have run this sample container, the device query, so it will tell us whether it's able to access this GPUs from the Nano. So if you see, it detected one CUDA capable device, Nvdia Tegra, and now it says the result is pass. So that means that it also tells us what are the different versions, like CUDA driver versions, how much is the GPU max clock rate, the L2 cache size, WAP size, and etc. etc. So now, since it has done that, and it says, I mean, the result is passed, so it's able to detect that device and the GPUs. All right. So now what we are going to do is we are going to create a YAML file. So let's do that. All right. So now, okay. So here, let me, all right. So let's pause here for a second. So, okay, so let's take a look at the YAML file for a sec. So this is the image that we're using is the DeepStream L40 container image that's available, one of the many. So it's a sample image that we are using, and we have deployed it in the K3s cluster. So when we create it as a pod and deploy it as a YAML file, it will automatically pull and run that container, and then we'll be able to query it and then do object detection, right? So this is the YAML file for it. And now let's go out and, right, so let's clear this thing, everything. And now we'll just apply the spot, right? So it doesn't take a while. Right, so if we do get pods, we'll see that the demo pod is now running. The other one that it shows is the one that we ran earlier. So now, right, so we are going to go in the container. We are going to unset the display since it keeps looking for a display even before it runs. And that's why we need to do that. And now we are going to run this DeepStream app with, so the config file or the sample file that we're using is source one towards the end, USB infrared net int 8, because that's the one that is available since we are using a USB camera, right? So the error that you see at the top is deserialized engineering failed. That's because it tries to look for the IIoT engine that's for the Xavier family of Jetsons. But then it switches to FV16 since it's a nano, right? So that's just something that we observed. All right, so once does that, we are going to see that the container is running and it says pipeline is running, right? So now it's running. So we are going to see how it detects the objects and how it runs all of this and does the analysis, right? So I'm going to switch to another video, and it's a handheld recording, so two of them, and we'll see the live feed that we talked about, and the already running video, and the camera is capturing that running video, right? So I'm going to switch over to that. Okay, so this is the video, and it's a handheld thing, so it will show us the pipeline running, and let me play it out. All right, so it shows that the pipeline is running, and now it goes to here. So let me pause it. Yeah, so it shows that it's aimed towards the parking lot. So it shows that there is a car, and it's able to detect that. So this is the HDMI display, and we'll also see the camera that's pointed towards the parking lot, right? And if you see a little closer, and we didn't plan that, but there is a second car that's in the background. So if I take it a bit behind, yeah. So we pointed it towards the parking lot, so it's able to detect this one, and I didn't see that there is another one here also. So it's able to detect that as well, right? Now, this is the live video feed that it was running towards, or rather the camera is pointed towards the parking lot, so it's able to detect it. And now we are going to see another one where the video is playing on a monitor and the camera is pointed towards that and how it behaves, right? Okay, so this is the second one. Here again, you see that the containers is running when it shows, and it's able to detect some of the frames. Now let's see what's happening here. So this is the JSON setup that we saw earlier. These are all the devices, but right now we have connected it to only a single one. It's connected via USB. And so this is the video that's running on the screen, and our camera is pointed towards this monitor. So there are a lot more analysis that needs to happen, but it's still all happening in the same thing. So it's a busy street. So you see lots of people that are going, and if you see it closer, here it's almost like no lag. So these are the two screens that you see. One is where it's recording, and here is where it's able to show and detect the objects. So let's see what happens on this side. So it's a busy street with different types. I mean, there are people, there are cars, buses, and things like that. So, and this is the display. So it's able to detect that there is a person, there's a car that's going in, even all these things it's able to detect pretty seamlessly. So this actually makes a compelling argument, and all of this is running on a K3s cluster, and with these Nvdia DeepStream containers that are running, and it's taking advantage of all the GPUs that are available through the Jetson family of things, right? So this concludes the demo, and I have one more slide to share. So let me go there. All right, so we are back on our slides. So, all right, so this is the last slide. So if you have any questions or any collaboration opportunities, you can reach us at sw-ecosystem@arm.com. For any Project Cassini resources and blueprints, you can check out this link. And for Parsec related information, you can check out the GitHub repo, and everything is available over there. So with that, I would like to say thank you for attending this session, and I hope you've learned something new. Thank you so much.